Hello, everyone. My name is Jacob Fine. I'm the president and founder of the Universe Discovery Project. Today, I'm here with Professor Matthew Johnson and my co-exec, Karina. Today, we're going to be talking about a theory of everything and addressing questions that relate to it. And now Karina's going to introduce herself and then Dr. Johnson. So go ahead, Karina.
Hi there, my name is Karina. I'm UDP's research executive, and I'm looking forward to a very thought-provoking conversation today. I'll pass it on to Dr. Johnson.
Hello, I am Matthew Johnson. I am a professor at York University in the Department of Physics and Astronomy, and I'm also cross-appointed at the Perimeter Institute for Theoretical Physics. I do research in theoretical physics and cosmology, and I'm excited to participate in this interview. Thanks for inviting me.
So I'm just going to start us off by saying, whenever we think of the world, we like to generally observe patterns and make certain analogies. The reason why we are even able to make these analogies in our natural world is because of a kind of repetition or a unity of principles. With that in mind, let's quickly talk about the history of finding a theory of everything, and why do we even have a reason for believing that it exists? So with that, I'll jump into our first question. Professor Johnson, what do physicists mean when they say theory of everything?
Yeah, so this term arose during what I would call a particularly optimistic time in theoretical physics that started maybe 40 years ago-ish, 50 years ago perhaps, where physicists were learning about the fundamental laws of interactions between the constituents of most stuff, which is particles, right? So, the universe, roughly speaking, we've observed 4 different types of forces. So there's electricity and magnetism. That's one we're all familiar with. There's the weak and strong nuclear force. The weak nuclear force is what's responsible for radioactive decay of particles, and the strong nuclear force is the glue that holds quarks together, for example, inside of protons and neutrons. And then there's the gravitational force, which of course we're all familiar with because we're not flying up into space as we sit here on Earth. And so, there was a time when we were making real progress on putting all of these 4 forces together into one single theoretical description. And the reason that, we had a lot of optimism at that time, and I'll get to why there's still optimism, but anyway, this was particularly like optimistic time, is that we figured out how to put 3 of these forces together into something called a grand unified theory. And so this is one single theoretical construction, so a set of equations, if you like, that could be used to describe electricity and magnetism, the weak nuclear force, and the strong nuclear force. Well, this was really exciting. The outlier was gravity. And gravity is kind of strange because, well, think about it, electricity and magnetism and nuclear forces, small stuff, right? So it's like, how do our atoms formed, and how are the nuclei inside of atoms formed? And so the natural language for that is in terms of quantum mechanics. So quantum mechanics is, the physics of the very small. Gravity, on the other hand, well, it's usually about big stuff. You don't really care about the gravitational force between 2 electrons because it's really tiny. You need an Earth amount of electrons to do something interesting. So it's different, right? It's the physics of the very big. And so, we were, as physicists, kind of stumped. How do we now, combine this 4th thing with these other 3 when we use quantum mechanics here and we use something else called general relativity here for gravity, right? So there's kind of like this incompatibility. And so roughly speaking, that's what physicists mean by a theory of everything. So there was a time when we thought we could combine all these four forces together into a single theory, or if you will, a single set of equations, right, that describe the interactions between particles, stuff. Just a few words on what that was. So, and still is, right, although there are many more approaches now. So broadly speaking, you need a theory of quantum gravity. So you need to combine quantum mechanics with gravity. And the bright idea that people had, kind of in the late 70s and early 80s, was instead of thinking about points, what if we thought about lines? The next most complicated thing. So usually we think about particles as points, but what if they were extended in some way as lines? And this is called string theory, okay? So instead of thinking about how particles interact, people started thinking about how strings interact, if strings are the fundamental components of nature. And it turned out that if we just shift our focus from particles to lines, it pointed a way forward to combining these four forces together. So it turns out you could have a quantum mechanical description of the gravitational force in terms of these strings or lines. And there was about a 10 or 15 year period where people thought they could figure this all out and find the unique theory of everything, meaning all the forces we know and all the particles we know. And then, well, that idea kind of blew up in our face, because we found out that the theory of quantum gravity is a different kind of theory of everything, meaning that in this idea where you have these lines, it turned out it was only a really beautiful idea, and it only really worked as a theory of quantum gravity if instead of the 3 spatial dimensions we see, there were 6 more that somehow we can't. Okay, and the most popular idea for ensuring that we can't see those 6 extra dimensions was to make them really tiny, so that you needed a really powerful microscope to ever be able to see them. And we just have not been able to build a powerful enough microscope, not even at the Large Hadron Collider, to see them. Okay, so we could hide them. But the thing that happened is we realized that there are many ways to hide them. And depending on how you hide them, it gives rise to a slightly different set of physics that we experience here in the 3 dimensions that we know and love. And so this theory of everything became a theory of everything, meaning that it predicted many, many, many different laws of physics. So it predicted everything. And this is kind of, I would say, an ongoing crisis. We don't know what to do with that. Like, okay, so what is the right theory of nature? Well, if we believe in this idea of the fundamental constituents being lines, it tells us that there are many, many possibilities. And so that's a bit of a historical picture of where this came from. There were these efforts to put the forces and particles into one description. That's what we called the theory of everything. But I would say that right now, it's not really clear that that is ever going to happen.
Great, amazing. A lot of stuff there to address. If you don't mind, I had a little follow-up to that, because you mentioned something. You addressed an interesting point in particular, which is the fundamental limits of knowledge, or the epistemological constraints that we have. And so you mentioned that in the theory of everything, it would have to explain everything that we currently know, meaning that we're always kind of like necessarily bound in our knowledge at a given time. So I kind of want to hear your thoughts on how the limitations of knowledge function and how they limit our ability to construct theory of everything in the context of physics. but also not only physics, because theory of everything can viewed in a more broader sense can include other disciplines as well. But in particularly about the limits of knowledge, I wanted to hear your thoughts on that. So.
Yeah, I mean, it's a theory of everything we know. And I think that is the best that anyone could ever hope for. We have learned a lot in physics, sort of about the ways in which things can go wrong or be different when we learn more. Yeah, so let's go back to gravity. Newton invented a great theory of gravity, and it worked for a really, really long time until we realized that, the orbit of Mercury is a little bit different than we thought it should be. And so we need to supplant this. I mean, the invention of the theory beyond Newton, which is Einstein's general relativity, is a little bit more than explaining a piece of data. I mean, it really was this kind of thought experiment that ended up panning out into something amazing. But anyway, if we take like a non-historical perspective, there's this thing that didn't quite fit Newton's theory. And we learned that there was more. There's this other theory, Einstein's theory of general relativity, that could predict that extra little piece of data. And it's not that Newtonian gravity is wrong, but it has a limited realm within which it can make good predictions.
Right, yeah.
So there's a technical term for that. We would call it an effective theory, okay? And pretty much all of physics is built on effective theories. And that is, up to if we check how much we can see, how much we can know, the best we can hope for is an effective theory that can predict all that we can see and all that we can know.
Right, and it kind of follows necessarily from the premise that we only know a finite number of things at any particular time. And if that premise is true, then necessarily any theory we construct can only be based on what we know at a time point t, and that's the effective theory. And that's not
yes and no.
Yes and no. Okay.
I'll push back on that, because a really beautiful theory is something that predicts what we know, or that explains what we know. Let me use a different word, but predicts something else, something that we can go to look for that confirms, yes, this is the right description.
Right.
And gravity, again, is a great example, right? So, very recently, we have just observed one of the predictions of Einstein's theory of general relativity, which is gravitational waves, observed by LIGO. So until 2016, for 100 years, 100 years, we had this extra prediction that was waiting to be confirmed so that we could really know if Einstein's theory of general relativity was kind of the right description of gravitational physics in different regimes beyond Newton. And so, that is the power of a good theory, or a good theory can be judged by something that not only explains what we've already seen, but makes an extra prediction, even if it takes 100 years to bear that out.
Yeah, so I guess I should have clarified a little more. I do agree with that, of course, 100%. But I was more addressing the power with which we can construct a theory is a function of what we know. That's true. And I think there's always a kind of a necessary need for having some ingenuity that goes beyond a little bit of what we know and make some extra claims based on phenomena that have not yet been observed, and postulates entities that have not yet been observed that can later be confirmed by experiment. So that's kind of, I understood, that's what I understood of what you were getting at with that.
Yeah, exactly.
And that's I absolutely agree. Yeah, Karina, did you have anything to add?
Yeah. So I do have a question there. So as you said, kind of Sir Isaac Newton's observations kind of links celestial and terrestrial gravity. So that was a very nice unification there. And also in the 1860s, Maxwell unified the concept of electric force and magnetic force, kind of saying that they're two sides of the same coin. And this basically explicates all of chemistry and a lot about light as well. So when thinking about what our next unification will be, by the way, quickly, is there a grand unified theory yet? Or
There's many.
Right, and one of them is string theory, technically.
Yep.
So I'm just wondering, we wonder if maybe there is a theory that the remaining forces, gravity, strong and weak nuclear force, and electromagnetism, if there's a theory of everything that can really account for all of them. So what are some reasons or signs that we can kind of suspect that such a theory actually exists?
Yeah, well, math. So these are kind of mathematical experiments, right? We postulate that the universe plays by the rules of logic and mathematics, and we see where that takes us. And we don't have any evidence that we need quantum mechanics to explain gravity from doing experiments. Zero. But we have lots of thought experiments, and we have lots of ways of just making a chain. Well, if I do this, it means this, and that means this, and that means this. Oh, quantum gravity, right? So
like a priori deduction from first principles. You postulate
right.
a bunch of premises, and then you move them around, and then they imply things like, by definition, okay, if this is true, then that, then that, then that. And that is interesting that you mentioned, because in the history of philosophy as well, there has been that divide between like empiricism of going out and showing how something can be done experimentally, and what were called rationalists, or people who thought that you could basically sit in a chair and just think of premises and deduce everything about nature from that. But I think, as you mentioned, there's a need for both. But I think what's the limiting factor is experiment, which I think you agree with as well, is what's always going to be the basis of science, is what you can show with an observation. But then, of course, that begs other epistemological questions about, like, okay, well, what if it's just physically impossible to demonstrate that, but it might exist still in some sense? So, there's a lot to talk about there.
I mean, I would agree. It takes both, yeah. And I think if you look at the history of physics, it's happened both ways. People have predicted amazing things by doing thought experiments, which were later confirmed. People have also looked at experimental data and come up with new ideas to explain what they see. And it's sort of the mixture of those two that's really led to progress. There's other ways in which even if you build theoretical constructions that don't get borne out in laboratory experiments, or it's just impossible to do that because it takes too many resources, or there's some fundamental limitations that you're up against. The novelties and inventions in mathematics that has come out of thinking about these things turns out to be really powerful and connected, both to pure mathematics, but also potentially to practical problems. Historically, also, if you look at, Einstein's theory of general relativity is a great example. There are these mathematical nuts and bolts lying around. We don't quite know what they're useful for necessarily until someone comes along and builds something really neat with them. So in that example of general relativity, it was the mathematics of differential geometry, and that ended up being a very powerful tool for building this theory that describes the physical world. So there's sort of, I would almost call it an experiment when we're building these theories using new mathematics or new concepts in mathematics. Those are kind of experiments too. Right. Just not ones in the lab.
Yeah, right. Karina, do you have anything to add to that?
Yeah, I'm just wondering, Professor. So another thing that I've heard of why such unification exists, or why we suspect that it does, kind of a clue, is that if you look independently at each of the major forces, their strength depends on the energy of which we study them at. So some get stronger, some get weaker. But then at a single energy, it seems like all their strengths, kind of their curves meet. And at a single hypothetical energy, by the way, like 100 billion times, I think, higher than what our best instruments can measure. But there is that point. So do you think like that's kind of strong evidence of there being potentially some unification?
If I could also add a little bit before you respond, just to build on that. What I think where we're getting at here is more like, can we be sure that such a theory is kind of out there for us to be discovered, or is it more of just like an effective process that is, I mean, Richard Feynman kind of described it well when he said, is it like an onion with millions of layers, and we're sick and tired of looking at all the layers, and you keep going deeper and deeper and it just never ends? Kind of like an asymptote. Is that the nature of what we're looking at? Or is it going to be like one day we're just like, aha, here it is, and all of you scientists now have nothing else to do because we're done? I don't think that makes sense. I think the asymptotic view that it's getting closer and closer over time might be more accurate. I was wondering what you think of that.
Your guess is as good as mine. I don't have much to add to that. Sorry, Jacob, but you just keep digging, and maybe you hit the rock some point, or maybe you don't. I don't know. Depends.
So maybe there might not be a rock. That's basically.
So now here's my question. Currently, the physics community, are they optimistic? What challenges are they facing? Of course, like the Large Hadron Collider, it can't even possibly measure such large quantities of energy. But what gives us hope, if there is any hope? What's kind of like the modern point?
Yeah. Well, I think there are a number of camps. I think there are, there's one viewpoint, which is, let's always keep looking in experiments, and eventually we'll find something new. And I think there's optimism there. I think that is a good bet. Okay. It's a good bet that if we keep building particle accelerators that can go to higher energies, or building surveys of the universe that can go deeper and see further, or we keep looking at black holes and how they make gravitational waves and merge and all this, like, we will find something new. I personally think that is a pretty safe bet, just because it's always happened before. Why now are we at the limit of finding something new? I don't think I have a good reason for that. So, that's one approach. This historical approach that I was talking about, this great sense of optimism that there was a center of the onion, if you will, going back to your comment, Jacob. I don't know that there is great evidence for that right now. I think that that hope has been dashed a little bit, just by the way things worked out. When we kept digging, we found out, it turns out, if we look at that, analogy, or that what you were describing, Karina, about, the forces meeting at some energy, that idea worked really great for 3 of the forces. But then I add one more, and that idea is not working so well anymore, in the sense that there's many ways to do it. It's hard to find a unique way to do that. The other thing that I think dashed a lot of hopes was the non-observation of something called supersymmetry at the Large Hadron Collider. We really built this machine not only to find the Higgs boson, which it did, thankfully we got there, but more importantly, to discover this extra thing called supersymmetry, which is, by the way, the reason that all those forces might meet at a certain energy. That's something that like guarantees that that will happen. And it's a really beautiful idea. It's also part of this theory of string theory. Um, and you know, I think the physics community was really hoping that we'd find it. We might be just about to find it, but if we do, it's going to be kind of a weird version of it because you know, some of the reasons for inventing this idea, well, it's getting a bit hard to rely on them because we haven't found it yet. Okay, yeah, there was sort of a strong prediction we should have found it by now, and we haven't. So you know, then I think that you know, that really killed, those things just kind of killed this idea that there's a center in the onion. And now, well, yeah, we're at a bit of a crossroads. I think you can think about the theory of everything now, that there are just many predictions, and try and make sense of that, which is something that I've been historically quite interested in. But yeah, I don't know. I think there is optimism that we'll find something, but I don't know that any of us really are very confident in claiming what we'll find at this point.
But okay, yeah, a lot of great points. Just to add to that a bit, I think what we can say, though, to be optimistic, is that if you look at the history of science since Newton and before Galileo, there has kind of been a progression towards more truth than there was before, right? So I think, having said that, there is a basis to say that there is a lot of unification that has happened. There has already been so much of it. And because there's been a lot of unification, does that mean necessarily that there'll be more in the future? I mean, not necessarily, but I think logically, like in terms of history, yeah, I would say I'd expect that to happen. So I guess what I'm saying is we've already come so far, and there's been a lot of unification, and we have sub-theories of everything, if that makes sense. So I just wanted to address biology because that's my area of interest, and that's where my degree is in. I would say the theory of evolution is a kind of theory of everything in biology. It functions that way, in that it's the kind of underlying principle for why life is the way it is. It's in other words, the history of how life came to be, in some sense. And I think that relates to physics, and it relates to other disciplines, because you could kind of view the entire evolution of the universe, the entire evolution of the cosmos, as being just one process of cosmic evolution from the Big Bang to the present, which includes the evolution of human societies in the Iron Age to the invention of the internet, but also the origin of cell membranes and the mitochondria, and and you go further back and you go up to the beginning, the origin of protons, the origin of the electromagnetic force, right? So that is, what do you think of the view that the theory of evolution is a kind of unifying, it functions as that, it functions as a unifying factor of cosmic evolution? And if so, is that part of the search for a theory of everything?
I mean, it's a paradigm within which you can explain many things we observe. And so if I were to make an analogy, it's less like string theory and more like the fact that no matter how much we learn, it seems like mathematics is a good description of the universe. It's a paradigm, it's this paradigm within which you can use to explain many things. Cosmic, I'm not sure I would use with evolution, although certainly, the initial conditions for life do have some sort of cosmic explanation. Although, and there it's, well, an exciting thing I bet you'll learn in your lifetimes is, a lot about the origin of life and whether or not it's happened anywhere else in the universe. I do think
Yeah.
with
I
the
should
observation
ask.
of exoplanets and many
Yeah.
other things,
Right.
there's really really neat stuff that's going to happen in that realm.
Yeah. I should add personally that the origin of life is a big interest of mine as someone who studies biology, and that being one of the main questions. My thesis is actually on it now. I'm doing an honors thesis on the origin of life that addresses the origin of life.
Mm-hmm.
And it's a big interest to me because partly it is really the kind of big bang of life in a sense. Although it was not sudden, it was likely a very gradual process of evolution, of chemical evolution that led to protobiological evolution and ultimately to protocells and life. Mm-hmm. So what's interesting to me is the kind of the parallels between biology and physics, in the sense that, well, I know some physicists might not like this analogy, but the view of galaxies are drifting further and further apart, so therefore they must have been all on top of each other. In biology, there's a kind of analogous view, which is that life is kind of evolving further and further from each other, and therefore necessarily they must have all kind of been on top of each other, like at a beginning to that, the origin of life. The beginning of that, giving rise to all the subsequent evolution and complexity of all the domains of life, I think parallels parts of cosmic. I know you don't like the term, but so parts of the evolution of the universe, and there's a kind of unity or unification to that. And so I'm wondering what you think of that analogy, and also of the idea that there's an underlying kind of like physical evolutionary process that explains everything, that unifies all the disciplines.
I mean, in some sense, is there an underlying thing that unifies all the disciplines? I do think that is the theory, whatever it is, of the fundamental building blocks and their interactions. But good luck explaining evolution of bacteria with those equations, right? I mean,
yeah, I know. Yeah,
it's kind of useless in that realm.
You need emergence.
Yeah, and I mean, even in physics, good luck really explaining at a fundamental level more than 2 or 3 particles. It's just beyond our ability, right? Even though the physics is all there, we understand it. It's cumbersome and it's difficult to apply in scenarios that are, involve many players, many particles. Yeah, so, if you want me to connect that to, the origin of life to the origin of the universe, well, I think there is somewhat of an analogy. There are a few viewpoints on how we think the universe might have come to be. And broadly speaking, you could classify them into it had to happen because of some, symmetry or some inevitable dynamics.
Right. Yeah.
Or it's accidental in a sense that there are many different regions where the universe looks different, and we happen to be in the one that is hospitable to life, right? And so hence we can observe it. And there's just no one to observe these other faraway places. So, okay, we're not there. So it could, to make the analogy then, I would say that the origin of life is less like galaxies drifting apart, therefore they must have been together, and maybe a little bit more like, is it an inevitable outcome of initial conditions and dynamics, or is it accidental that it can happen in some scenarios by chance or not?
Right, no, absolutely.
Yeah, right?
That relates to the argument of chance versus necessity. Is there a kind of, were things meant to be a certain way because of some fundamental principle of the universe, basically? Like, I would argue that there are some things that are necessary. Like if you flip a coin an infinite number, or not, if you flip a coin a large enough number of times, necessarily half will be heads, right? Assuming that there's some constant, condition that, or whatever, I mean, I should say, in normal conditions, right? So there's a kind of fundamental probability rule to that, which governs the universe.
I think that's a great example because it doesn't have to happen. It's just likely to happen.
But it's likely to happen. However, it's likely to happen if and only if this n is large. And it's necessary to happen if and only if n is large. So as n gets bigger, as the number of planets gets bigger, then the chances of there being life on one of them is greater. And then the question is, does it approach 100% once n is really big? So if things have just been going on kind of forever, then necessarily one time something will happen, right? And that is kind of necessity in a way. So yeah, I don't know. What do you think of that?
Well, that could be the way the universe works. That's this accidental origin, right? That there's many coin flips, and therefore you will find somewhere in the universe that, given there can be a variety of initial conditions, there will be somewhere that looks like what we see.
Right, but what I haven't understood about that view isn't that view also saying, by definition, that it's necessity? Because you're saying that it is true that there's a big sample size, so necessarily one will happen. So it's not really chance. It's more of just like a principle of probability that dictates an outcome because the n is so big, right?
The difference would be a fixed coin and a fair coin. So postulating a symmetry that dictates the early universe had to be a certain way it's like a fixed coin. It's like I'm going to flip it, but you know what? I'm going to get heads every time. So I'm guaranteed by the properties of this coin, or by the properties of the laws of physics, that every time I try to make a universe, it looks exactly like the one we see.
Right? Yeah, right.
Versus a fair coin, where there's a wide variety of possible outcomes. And well, yeah, if I flip the coin enough times, I'll see any sequence of heads and tails I want. It is a probabilistic certainty.
Right.
But you could see the philosophical difference.
I do see there's a nuance in that.
Is there one possibility, or are there many possibilities, right?
Right. I hate to be the guy who says it's all semantics, it's all a matter of definition, but it does seem like there is a valid concept of probabilistic necessity, that the laws of probability they kind of dictate a form of necessity in some sense when n is large, basically. Yep. That's in fact why they are the way they are. That's what they mean. That's what it means when I say the odds of an event are 1 and 2. It means that if n was infinite, then half would be a certain way, right?
Yeah. So if you had to take a personality test that said, I like the multiverse and I don't like the multiverse, you have just checked the box, I like the multiverse. My personality is compatible with thinking of many possibilities and giving up on the fact that, in fact, there might be a theory of everything. It sounds like you would really like this idea that there are many possibilities, and we happen to be inhabiting just one of those possibilities.
Yeah,
but if you gave the same personality test to the group of physicists, they'd be pretty evenly split, I would say. Some would be pretty comfortable with that idea, and many of them would be totally uncomfortable with that idea. They really like wedded to this historical, hope that we could really find what I originally introduced as the theory of everything, the inevitable thing, the center of the onion.
So, like Einstein would have probably said that.
Yeah, exactly. Einstein would have been all in on that. Yeah.
Yeah.
God doesn't play dice, right? That's the famous quote.
Right. But the thing is, like, what I'm trying to argue for a kind of hybrid view, which is not entirely chance and it's not entirely necessity. I'm trying to say that when I said probabilistic necessity, that necessity evolves out of chance. That's what I'm really saying. So like there are certain things that have to be a certain way, can't be otherwise.
Yeah.
So I would bet my money as a biologist that if there's life anywhere in the universe, it would have to base itself on some atom that can form four bonds with other atoms. So carbon, that's why life is based on carbon, because carbon has this inherent property that it can do that. So, whether there's some other universe out there in the multiverse, if there was to be something equivalent to life, I would bet that it necessity in terms of that, it has to be based on something that is like carbon in some way. Now, a particle physicist might disagree with me, but I think that to get complex molecules, which I think is another necessity of life, you kind of need to have something like carbon. And that's where you get into necessity. And that's kind of consistent with the Einsteinian deterministic view of the universe. Karina, is there anything you wanted to add to that? I'm sorry.
It's a very, very interesting discussion. And the idea that the multiverse would kind of remove the need for a theory of everything because we're just one in many possibilities. It's very interesting to think about. But another thing that's been on my mind, and I just want to bring it back to kind of our original idea of a theory of everything, is so if we go really small to the quantum mechanical level, we find that really small, really small things are difficult to observe with our instruments because actually the act of observing them disturbs them. So that's like a barrier there, like an asymptote.
That's an epistemological constraint.
Right. And then on the other end, if you're looking at really large phenomena, for example, like the speed of light, like we physically can't get to the speed of light. And then a third thing that I want to say is that we'll never be able to achieve Planck's constant, that huge number of energy level with the Large Hadron Collider. So does that mean that there is a dead end? I really want to ask you that, Professor. What do you think?
Yeah, there is a dead end in a way. So if we think about traditional experiments, let me talk about two dead ends that are actually predictions of gravity. So if I take two particles and I smash them together, eventually their energy will be so great that they'll form a black hole. And it turns out black holes are really boring. They can be described by only three numbers: their mass, their spin, and their charge. And so all of the information about quantum gravity that I might think I'm going to learn by smashing two particles together might be thwarted by the fact that I end up just making black holes, which are really boring objects, and then they shield all the interesting quantum gravity stuff around them because light can't get out to tell me about it. So that's one way in which, the theory of gravity kind of predicts its own, what's the word I'm looking for?
Its own incompatibility with the other forces.
Yeah, it like hides itself. Okay, that's a pedestrian way of, like eventually it will hide itself. So it might be really hard to observe quantum gravity even if the Large Hadron Collider could achieve energies of M Planck. That's a distinct possibility. The other way that gravity is kind of funny and thwarts what we think we might be able to learn is, so right now we observe that our universe is expanding, but it's expanding faster and faster with time, so it's accelerating.
Accelerate, yeah.
And our best reason why is that there is this thing that we need to add in Einstein's equations called a cosmological constant. Okay. And in a universe with a cosmological constant has the following really kind of puzzling and frustrating property. So if I look around us in our local universe, there are things to which we are gravitationally bound. We are gravitationally bound to the Earth. So the expansion of the universe ain't going to touch us. Our Earth is gravitationally bound to the sun. Expansion of the universe doesn't matter for that. Our sun is gravitationally bound to the Milky Way galaxy. But if we go further, a few galaxies out, past something called the local group, then the binding energy due to gravity is not enough to fight the expansion of the universe.
Right, yeah.
And so our future, if we go to the future, these things that are not gravitationally bound to us will get further and further away. And in fact, in this universe undergoing accelerated expansion, the further something away from us, the faster it's moving away from us. Mm-hmm. And eventually they will be moving away from us faster than the speed of light, which means that we cannot see them. We will no longer be able to see these other galaxies.
Right.
And so if we were born like 100 billion years from now, so that there was enough time for what I just described to happen, we would think the universe was really small. It would just be us and a few galaxies around us. We wouldn't be able to detect the expansion of the universe because there are no galaxies far away moving fast away from us to see. And our viewpoint, our picture of the universe, our theory of the universe, if we had to come up with it from scratch at this time, would probably be totally and completely different. Because we just see these few galaxies around us.
Sorry, Karina, did you have a question?
Yeah, just quickly, would cosmic background radiation be any indicator of expansion or no?
Well, it gets colder with time. So if we waited, this extreme, amount of time in the future, then it's probably too cold for us to detect.
You know what that's very similar to? So imagine you're a set of twins, or imagine a set of twins sitting in a mother's womb, and they're having a conversation, and they think, oh, well, this is it. This is the life, but they aren't aware of the world that's around them. That's just beyond their capabilities.
Yeah.
Okay. So it's just the epistemological constraint of, like, by definition, we're not in the big enough scope to see that, right?
Right, and like it's physically impossible to be in a big enough scope to see it if we wait long enough in the future.
That's like
the interesting thing.
How long are we talking?
Yeah,
sorry.
like, hundreds to thousands of times the age of the observable universe so far. Mm-hmm. So, when the universe turns, I don't know, 100 trillion years old or something, then it's probably going to be really hard to see stuff.
Makes sense.
We're getting close to time, so I think we should wrap up with maybe some concluding remarks. Sorry, I just wanted to pull up the questions so to make sure we covered everything. Mm-hmm. I guess a brief question would be, Dr. Johnson, in your view, what do you think, or what do you think the end goal of science is, or the end goals of science are? Not just physics, but science in general.
There are no end goals. It's a journey.
It's a dynamic process.
So it is. So I think I agree with that view. I think it's really about the process of learning and not what you've learned at the end. I don't know if you agree with that, but that seems to be what you suggested.
Stuff, and we'll always learn more stuff, and I don't see there being an end to that.
So it is in that case like the onion, that you're just peeling away at its layers again, more and more, until you never know. You don't know if there's a core at the end of it or not. But
I mean, it might get too hard to make progress. That's a possibility. But
yeah. We're trying to predict the future of science, and that's kind of hard to do.
What's the place to be right now in science? Especially when it comes to studies of our universe, do you think that it's math? Like, do you use math a lot in your day-to-day?
Yes, I think there are many exciting places right now. We just discovered gravitational waves. There's this whole new field of gravitational wave astronomy that was just born, a few years ago. There are enormous technological leaps that have happened, both in computation. So that helps us analyze huge data sets to learn new things from them, but also like new telescopes, new detectors for particle accelerators, new experiments we can do in the lab, like not the Large Hadron Collider, but like in Petri science and engineering, that can be used to find physics in new and creative ways. not by making lots of energy, but by putting lots of things together. So, new approaches, new ideas. I think it's like a really interesting time, because also there are theoretical puzzles that we had been expecting to find certain things for the past 30 or 40 years, and now we have these machines that are supposed to find them and they're not finding them. Like this idea of supersymmetry I was talking about. So that's a mystery. What is responsible for this accelerated expansion? What is the dark matter? We could just talk for like an hour about open questions right now. And we could spend another hour on all the exciting ways people are coming up with to try and answer those open questions. So, it's like a really interesting time where we can both like build things to learn new stuff. And also there are these really interesting mysteries that, are out there that we're trying to solve.
They remain to be solved.
Yeah.
Amazing. Okay. I think that was
to be continued.
I think that was a great way to end. There's lots of mysteries to be solved. So with that, Dr. Johnson, I'd like to thank you for your time.
Yeah, thanks.
And this was really great.
Okay, great. Well, thanks for doing this, and let's do it again.
Best of luck in all your endeavors, Professor. Thank you. Thank you for your time.
Okay, I'm going to stop recording. Thank you.